two top years of potential excitement for the discovery of new particles at the LHC. But what's gone on even up to now has shown that 25, 30 years of many very brilliant people thinking about what we might see. The experimentalists are not showing us what most of the community thought would be happening. This is, I think, something profound and important. 6,000 people have spent decades of their lives telling a big group of theorists that for the second time in the last 30 years, some very super basic zeroth order fact about the world. We live in a big macroscopic universe. The universe is big. It has large things in it because gravity is weak. We thought we had some zeroth order pictures for why both of these things were true. In the case of the cosmological constant problem, you polled a random theoretical physicist in 1995. They would say there's some deep magic mystery mechanism that makes the cosmological constant exactly zero. And in the same year, they would tell you, and supersymmetry solves the hierarchy problem. Okay? And neither one of those expectations, well, for sure, it looks like we do have the cosmological constant, so that one was wrong. And whether or not we discover some version of supersymmetry, whatever it is going to be a little weird, either very weird or a little weird, but certainly not what people expected. Now, this is great news for you if you're a young theorist, because it means that there's no competition. Okay? There's a whole generation of people who had a really great shot at it and blew it. Okay? And I'm part of that generation of people. Okay? I mean, I think it's very important. I mean, I really wake up every morning thinking, my God, it's crazy. What's going on? We haven't seen what we expected. By the way, we weren't nuts. I mean, we weren't. In the case of the cosmological constant, we were perhaps nuts, because there was no actually concrete picture for the magic mystery mechanism that might make the cosmological constant zero. But in the case of the hierarchy problem, we're not nuts. I mean, there were these very compelling hints. There's the picture of dark matter, supersymmetric gauge coupling unification. Why the hell would these things fall in your lap? And there's always been this tension driving physics beyond the standard model. Always, from the very beginning, that on the one hand, you think because of reasons of naturalness, we should see lots of new physics. On the other hand, where is the evidence for this stuff? First, indirect. Very early on. Why didn't we see large baryon lepton violation? Why didn't we see flavor-changing mutual currents? Very early on, those things were thought of as, very early on, they were thought of as not as problems, but as opportunities. We would be learning something about the structure of the physics of the TeV scale. But things keep going on and on and on. You don't see direct evidence. You don't see evidence for, let's say, superpartners at LEP or at Petra. They could have easily, I probably don't even know what Petra is. Okay? I hope you know what LEP is. Okay? So, it's not the situation to the thoughtful people, I think to the people who have wrestled with the question of physics at the TeV scale their entire lives. It is not that it was, oh, rah-rah, obviously everything is obviously okay, we know what's going on, and then the LHC, boom, that's where the surprise started. No, people were already puzzled and surprised and slightly worried, not maybe very worried, but slightly concerned. Why aren't we seeing all these states if they should be around already after LEP? Okay? But what we don't know is if there's something a little wrong or very profoundly wrong with our picture of what is going on. And that's why we need all the help from experiment we can get. Whatever we learn, if we see some new particles, great. If we don't see new particles, it's a more profound challenge. It's a more profound challenge to our basic understanding of effective field theory and of quantum field theory. I think a very good analogy is it's like not seeing the ether a little over 100 years ago. Okay, that was an example of something where all the most brilliant people of the time thought it was obvious that such a thing would exist, and they were all wrong, despite the fact that it was not a stupid idea. It was actually a very useful idea, and it propelled people in roughly the right direction, but in detail it wasn't the right idea in the end. Maybe that's what we're starting to learn with both these big hints from the cosmological constant, and so far from the absence of any new particles at the LHC. I should say, my own private, personal point of view, and it's my sort of canonical fallback to what I think might be going on, is that there is a picture picture that not just I know, many people stumbled into it, but Savasopoulos and I advocated around 10 years ago, that there might be a picture of the world where all these hints, both in one direction and the other, both in the direction everything is great, supersymmetric coupled diffusion, dark matter, all these positive hints are still correct hints, but they're being misinterpreted, while explaining why we didn't see FCMCs and all these other direct production of the new particles, which is this picture of split supersymmetry. So that's a picture where all the hints could be true at the same time and just be interpreted in a different way. Made a prediction that the hints should be between 120 and 135 GeV. Okay, it's not a very detailed prediction, but at least it's not dead already. The only reason for there to be particles at the TVs here on that picture is WIMP dark matter, and that may or may not be accessible to the LHC. So that was just true from the beginning. But that's my fallback position only because we don't know anymore. But what I would emphasize, and just coming back to saying it again, we're learning something deep and dramatic about the world. There are 6,000 experimental colleagues who have busted their butt for decades to hand us a big surprise, and we should wrestle with it and we should think about it. Okay? But for that reason, for that precise reason, especially given that I have 3 hours, I don't want to talk about any particular picture of what physics beyond the standard model might be. I gave you my own prejudice for what might be going on. But really partially because there's no, especially as we're coming to the hour where we're really going to learn in a sharper way what's going on. I think we should really let our experimental friends do the talking for the next 6 months or so, and then have a real period of reckoning after Morio and start really thinking about which way the data is throwing us. So what I wanted to do, what I thought would be perfect to do in 3 hours of lectures, is talk about something else, a very basic topic, a fundamental topic, something that's not as widely known as it should be, and also something which has just very recently an extra twist to it that allows us to make it more complete. So that's my title. I want to talk about collider physics from the bottom up. This is secretly also some lectures on how to think about scattering amplitudes, and more generally quantum field theory in a different way. But in fact, from the very beginning, the questions that motivated this whole subject were questions about the scattering at colliders. You probably know these famous things that if you open up Peskin and Schroeder and you copy out the finding rules and you want to calculate 2 gluon to 2 gluon scattering, okay, we put that on problem sets when you're in grad school, and maybe you can get it right. Okay? If you want to compute 2 to 3 gluons, it's 50 pages of algebra. It's a horrendous mess. Okay? 2 to 4 gluons, 200 pages of algebra, horrendous mess. And yet people found that these expressions collapsed to incredibly simple expressions, almost exactly 30 years ago, in fact. A little over 30 years ago, this subject really started with Steve Park and Tom Taylor at Fermilab, who found for some processes, for some gluon scattering processes, these ridiculous simplifications. And back then, people didn't realize really that it was the tip of a giant iceberg. But through heroic work of many groups of people, from this particular line that I'm talking about, people like Byrne and Dixon and Kossauer and others, slowly emerging. It's not just a bunch of tricks, that there's really some totally different underlying set of ideas and structures and really new deep mathematical structures underlying not fancy schmancy physics in 11 dimensions and Calabi-Yau manifolds and all that crap, but just good old-fashioned gluon scattering. Okay? Quark gluon scattering of relevance to hadron collider physics. So that's what I want to talk about. But there's been, well, one thing is first, sometimes somewhat sort of fancy sounding things show up in these subjects. There are these interesting variables. They're not very fancy, but we'll talk about them. There are spinor helicity variables that are useful for talking about the scattering of massless particles. But then you hear about these things, Grassmannian, some algebraic geometry, blah, blah. It sounds a little bit fancy. On on the one hand. On the other hand, a lot of development has been mostly about things like gluon and graviton scattering, massless particles. Some of the formalism is seems wedded to the scattering of massless particles. And very often I'll give talks about this, and some of my more distinguished senior physicists would come down and say, can you compute TT bar production in this way, and so on. You know, what about massive particles? What about this? What about that? And I would always say, well, the formalism hasn't been completely developed. I'm sure it's possible, and so on. Anyway, for totally different reasons, and other people have worked on this as well, but for totally different reasons, just in the past few months, some of my collaborators and I have been motivated to develop the formalism for massive particles as well. Okay, so that we can really talk about the entire subject. We can really talk about all of standard quantum field theory, standard model physics, the whole thing. We can talk about it from the bottom up. Okay? And learn how, starting from nothing other than the basic principles of Lorentz invariance, translation of Lorentz invariance, Poincare invariance, and unitarity, that those are the rock bottom principles that together, once you specify the quantum numbers of the particles that you're talking about, largely specify how they interact and scatter. So I want to describe that story to you now in these lectures, and especially now that we know how to talk about it usefully for massive particles. By the end of the lecture tomorrow, you'll be able to sit down and by hand compute any 2-to-2 scattering amplitude in the standard model you like, without touching the Lagrangian, of course, never mind that, but without, of course, not touching mad graph, not doing it, just at tree level, of course. But actually more than that. I mean, maybe you don't care about that so much, but let's say, just to give some invitation, let's say you're a beyond the standard model person and you're interested in the existence of some spin 3/2 excitation of the top quark. Okay, so that might even happen in various composite models, right? Maybe there's some workspace, there's a spin 3/2 excitation of the top quark, so you want to know what is the rate for, what is the rate for, let me do a random example, any quark, okay? Let me do an example. So let's say you have gluon, quark, goes to this spin 3/2 excitation, and the spin 3/2 excitation decays to a kk graviton and back to another quark. Okay. So that's an example of, maybe you care about a process like that. Now, how many people would be a little intimidated to think about how to calculate that, right? Okay. Very good. By the end of tomorrow's lectures, we'll just write down the answer. We'll just stare at it, think, and we'll write down the answer. Okay. That's going to be and you'll be able to do that for anything. In fact, all the things that involve massive particles like that, those are the easy things. Okay? In fact, the hard and interesting things will involve the massive particles. That's actually what we'll start with today. Okay, so as I said, this is really possible to talk about in this span of time, and I think it's fun. So that's what we'll do. All right, now let me start with an invitation. Let's say that we're interested. Just to give some idea of what it is that we're after. Let's say that we're interested in scattering amplitudes involving just scalar external states. Okay, that's not so relevant in the real world because we don't really do Higgs scattering. But imagine that we have scattering amplitudes only involving external scalar states. Okay, so there are some. So the first thing you think about when you think about amplitudes is the simplest amplitude is a 2-to-2 amplitude. We'll come back and correct that a little later because the really fundamental amplitude is a 3-particle amplitude. That will be the big focus of our study in a little bit. But the most naive one is a 2-to-2 amplitude, and the particles may or may not be identical. It doesn't really matter. What I want to ask is, what can we say the amplitude looks like just on completely general grounds? First, let's just imagine what it can look like. Okay? So there's some function of s, t, and u, the Mandelstam variables. You guys all know what s, t, and u are? Okay. Okay, so you have some function of s, t, and u. So what could it look like? Okay, so let's just imagine what's the absolute simplest thing the amplitude could be. Absolute simplest. Okay, rational function's already pretty fancy, but thank you. But yeah, so, okay. The absolute, 0 is the absolute simplest. Okay, very good. We got that out of the way. Okay, so after 0, it could be a constant. It could be a constant. Okay, now, what could it be after a constant? It could be, I don't know, something times s plus something times p plus something times u. Okay, and it could be something s squared, p squared, u squared, blah, sp, blah, blah, right? That's the simplest it could be. In other words, the amplitude could just be just a smooth analytic polynomial function, right? And, okay, very good. So that's the very simplest kind of function the amplitude could be. Now, a theme in these two lectures is going to be that we don't ever need to refer to a Lagrangian. Certainly in perturbation theory, okay, we don't really need to refer to a Lagrangian. So the most extreme version of a talk like this will be to constantly go and never talk about the Lagrangian, but just in order to help build intuition, we're going to pause every now and then and talk about how we would interpret what we're seeing from the Lagrangian point of view. So let's do it here, right? What do these things mean? Well, this is what experimentalists don't care, thank God, they don't care about Lagrangians, so they just measure stuff. So they measure an amplitude. It's theorists who interpret it, oh, what we're seeing is a Lagrangian so-and-so property. So let's say that's the amplitude the experimentalists would give us. What Lagrangian would a theorist invent? Okay. So what would you say from the first term? You would say it's a phi to the 4 theory. Okay, you say there's some c phi to the 4. Okay? And then what would these things be? Those things would be if you had some derivative interactions, right? So maybe you have some phi squared, d phi squared. Okay? Right. And actually you have to be careful, if all the scalars are identical, if there's really only one scalar here, let's say there's only one scalar. You see, this thing would give you, definitely, there's two derivatives, so it definitely gives you something that goes like s and t and u. But let's go up here and imagine all the scalars were identical. If they're identical, there has to be a symmetry between sp and u, right? So in that case, this thing, so let's say if identical, then A would have to equal B would have to equal C. And so, but s plus t plus u is equal to 4m squared, right? So s plus t plus u would be a constant. So already we see something a little interesting. It looks like this is a new kind of amplitude, like it has an s and t and a u in it, but it's just absorbable into a change of what we mean by the constant. Okay? So why is that? Here I just wrote down a Lagrangian, phi squared d phi squared, right? That seems to be an interesting Lagrangian. Why isn't that giving me some new kind of amplitude? And this is the earliest lesson that the Lagrangian is misleading. Okay? Let's look at this thing again. If I look at 1 plus some constant phi squared times d phi squared, just for a single real scalar field, right? If you look at this and you ask, what are the amplitudes associated with this theory? Okay, looks like it's interacting, right? But if you compute the amplitudes, you'll find that they're 0. Okay, it's a little exercise you can do. The amplitudes are actually 0. It's sort of very easy to see why, because when you sum over the places where the derivative act, you get s plus t plus u. Okay, and if they're massless particles, because I didn't write down a mass term here, I would get 0. Okay. So a Lagrangian can be misleading. It can look like it's interacting, but secretly be non-interactive. And why is that? It's because you can do field redefinitions. Okay? If you perform a field redefinition, we can change what the Lagrangian looks like. In fact, we can do a field redefinition that turns that into a free theory. I encourage you to do it. It's kind of obvious what field redefinition you have to do. Okay? But of course, the physical amplitudes don't care about how you decided to associate the particles with the fields. That's the earliest indication that the Lagrangian is not an invariant concept. You can do field redefinitions while keeping the physics space. Right? So you see, so already we see something interesting. Even if you say, here's the amplitude, what is the Lagrangian that goes along with it? There's no such thing as the Lagrangian that goes along with it. There's an infinite family of Lagrangians that differ by each other by field redefinition. Okay? So already, even in this most trivial case, we see the advantage of thinking directly in terms of the amplitude, because that's the actual physical thing. Okay? Is that clear? Is that little example clear to everyone? Very good. Okay. But now let's go on. So what's the next most complicated thing that the amplitude could look like? Okay? So here it looks like just a beautiful analytic function. Let's say the particle is massless. Okay? It's a beautiful analytic function. So what's the next most complicated thing that it could do? It could be there's this infinite power series, which you could think of as more and more higher dimension operators if you're thinking in Lagrangian language. But it could be that, well, the power series has a finite radius of convergence, right? And that's because you hit a pole somewhere, right? So that's the next most complicated thing that we can happen. We can have poles. So I could have a pole, like something like 1 over s minus some m squared, right? And upstairs I could have some function of p, well, I could have some function of s, p, u is minus s minus t, so I can always, if the particles are massless, so I can always imagine it's a function of s and t. All right? And then similarly, t channel and u channel, whatever. Okay? And in fact, you see, I only know any dependence on just s here. I can, if there's any, if I'm imagining this is some kind of polynomial in s and t, any dependence in s, I can always expand in powers of s minus m squared. And that would just bring back things that look like polynomials. Okay? So what's really invariant about this is what's going on the residue at s equals m squared. So I might as well just think of this as a function of t, okay? Because s is really locked to an m squared. And if there was an s up there, again, I stress that I could always rewrite it out in terms of things that look like that. Okay? Okay, so that's the next most complicated thing that we could imagine having. The amplitude could have poles. Now, what do these things correspond to? Again, in Lagrangian language. So here, they correspond to just having the field phi and nothing else, and having various interactions for it, various higher dimension operators. This corresponds to what you think of as tree-level exchange of some new massive particles. Okay? The fact that there's a pole means that there's something that's not the particle that you were talking about. There's a tree-level exchange of something new. And so if we now say the fancy word that you said, rational function, right? If we're dealing with amplitudes that are rational functions, that means they look at most like polynomial over polynomial. Okay? Then that corresponds to the world of amplitudes involving tree-level exchange of the particle you have and perhaps other particles. Okay? Now, in the limit where there's really a weak coupling in the underlying theory, you can take in your mind the limit where that coupling becomes arbitrarily small, and then this is what dominates the amplitude in that limit. Okay? Now, beyond here, of course, we have more complicated things that can arise at loop level. And for example, we can have logarithms of s over some scale and so on. Okay? And what's important about these, I can get things like that, or dilogarithms even at one loop. Okay? Okay? What's important about these things is that they have branch cuts. They don't just have poles, they have branch cuts. Okay? And when you have a function that has a branch cut, and you have an amplitude that has a branch cut, well, first let's talk about just the simpler case of the pole. It's a crucial property of amplitudes that the real physics of locality and unitarity is sharply reflected in the singularity properties of the amplitude. Okay? That's physically obvious because, again, why is the amplitude becoming large? It's because there's a resonance and you're actually producing the particle. Okay, so the residue, how it's becoming large, should reflect the production cross-section for making the particle. Right? And that's what we learned from the optical theorem. The imaginary part of the amplitude is related to the total cross-section. And if we remember following Feynman that we should put 1 over epsilon down here, then the imaginary part of 1 over s minus m squared plus I epsilon is the delta with pi's and stuff. There's the delta of s minus m squared. Okay? And that is indeed telling us that that imaginary part is telling us that we are producing a particle at that mass. Okay? So that's the imaginary part of the amplitude is giving us the cross-section for producing the imaginary part in the forward limit of the amplitude. But anyway, when we go beyond the tree level, then we get more interesting we get more interesting analytic structure, not just poles, but we can have branch cuts. But it's the same story. The imaginary part, or really it's really literally the imaginary part, there's a log minus s there. Okay? So the imaginary part there picks up an I pi. Okay? And the imaginary part is always telling you that you're producing particles, but now, instead of getting a pole, we have a branch cut. And the discontinuity across the branch cut is proportional to, again, telling us about now pair-producing particles, which we're running around at one loop, let's say, in order to make that. Okay. But we're going to restrict ourselves to talking about the very lowest order in some underlying imagined weak coupling expansion, where we're only talking about trees. Okay? And so we're only talking about amplitudes that have poles and nothing else. Okay. Okay, so now a little invitation. Let's say that someone told you there's the scalar, maybe the Higgs, but we're not going to do Higgs-Higgs scattering. But let's say there's a scalar and it couples to a spin 7 particle, a massive spin 7 particle. Okay? And you want to figure out what does the cross section look like. You want to look for phi scattering. Okay? What does the amplitude look like? How many of you would be scared, again, by the fact that you have to deal with the spin 7 particle? Okay? We're all scared. Very good. And why are we scared? Why are we scared? Because we imagine, oh, fuck, A mu, what are we going to do in the Lagrangian? A mu 1 up to mu 7, then what? D mu 1, what are we doing here? Right? Phi, D mu, and then maybe you have to put these little forward backwards on them because people tell you need to do that for some reason. Okay? And then God knows, why do I put one here? It just looks a little bad, right? It looks a little confusing. Actually, this is the right, it's not so bad. But anyway, you're not immediately thrilled, right? You're not immediately happy. Okay? In fact, in the case where we have external scalars, what we're going to show now is what can the 2 to 2 amplitude look like in complete generality. No matter what's going on, we don't have to touch a Lagrangian, we don't have to look at anything, we can just write down the answer. Okay? And this case is relatively simple and familiar and is very close to what you learned as an undergraduate about the partial wave expansion. Okay? Except the partial wave expansion we learned in non-relativistic quantum mechanics. Actually, in this case of scalar scattering, the passage to relativity isn't such a huge deal. It becomes a bigger deal when we talk about massless particles and helicities and all that. That's what the rest of the lecture is about. But I want to talk about it in the language that the particle physicists would talk about it. If you forgot about partial wave expansions and Legendre polynomials and Kekima, don't worry about it. We're going to see it from the bottom up. Okay? We're going to see it from the bottom up now, and we're going to just write down the answer for what could the most general possible 4-particle scalar scattering amplitude look like. In the process of doing this, you'll get the idea for what's going to drive the rest of the lectures, and we'll do the rest of the lectures from a more principled point of view. This is going to be a little bit of a half and half, formalism. Okay, so let's think. Well, the easy part was a Jacobi polynomial, so that part we have under control. The hard part is what should the poles look like? Can I just write down any old random function of t upstairs? Okay. Can I write down, here, is this a possible amplitude 1 over s minus m squared t cubed minus t squared? Okay, that would be units. Okay, you're going to make me put units, fine. Okay, t mu squared. Is that allowed? Is that legit? Does anything go, right? What are the rules? That's what we're now going to figure out. Okay, but the key point is what's going on near the pole. What's going on near the poles? We have to have a physical interpretation for the residue on the pole. As we approach the pole, it has to look like 1 over s minus m squared. But what multiplies the 1 over s minus m squared near s equals m squared, this is the key property, is that unitarity implies factorization. So what it means is that this 4-particle thing, as let's say S12 goes to 0, normally S12 goes to m squared, sorry. But this has to go like 1 over s minus m squared times this guy. So whatever particle, heavy particle we are making, we have to have the 3-particle amplitude for producing the particle and decaying it on the other side. Okay? So this already makes you think about the concept of the 3-particle amplitude as the more primary thing. Now, that, maybe it sounds like you're making too big a deal of this. Well, of course you talk about the 3-particle amplitude all the time, z to e plus e minus. There's a 3-particle amplitude. But if you think about it in your courses, we have a kind of a schizophrenic attitude towards the 3-particle amplitude, because we talk about it for things like z decay, but you never talk about a 3-gluon amplitude. Right? Have you ever heard of a 3-gluon scattering amplitude? Why not? Because for massless particles, it looks funny, right? For massless particles, just the kinematics means that if you have a massless gluon, it can't split into 2 other massless gluons unless they're exactly collinear. And then it's not 100% obvious, but if you just, stare at the finding rule, that amplitude is actually 0. Okay? Rigorously 0. We're going to come back to this. In fact, we need to think about the 3-particle amplitude as the fundamental object that's going to drive everything for both massless and massless particles. But in this case, with a massive particle on the inside, it's not even that mysterious a thing. It's a quite familiar thing. Okay? So let's think about it. All right. But you see, no, there's no Lagrangians here, right? It's just saying that whatever this amplitude is, it has to factorize into a 3-particle amplitude on one side and the other. It's still about the amplitude. So now we have to learn what does the 3-particle amplitude look like. Okay, now you might think, still for the 3-particle amplitude, I have to go back, I have to write down a Lagrangian, I didn't even finish doing it, I have to follow the Feynman rules and get the amplitude. But we don't. The reason we don't is that what's special about 3 particles is that 3-particle amplitudes are completely fixed just by symmetries, okay? And nothing else, up to the strength of the coupling constant. And let's think why that has to be. What could a 3-particle amplitude possibly depend on? Let's think about that for a second. A 4-particle amplitude can depend on S, T, and U. Okay? What could a 3-particle amplitude possibly depend on? Okay. Is there any analog of S, T, and U? Sure, I can say it depends on P1 plus P2 squared. Okay, but what is P1 plus P2 squared? Say we have 3 particles. 1, 2, 3. Are there any kinematic invariants that we depend on? Well, let's write them all down. Well, there's P1 plus P2 squared. Oh, but that's just negative P3 squared. That's just the mass of the 3rd particle squared. Everything is a constant. There are no kinematic invariants. No analog of S, T, and U. So, we've already learned something slightly cool. What's the 3-particle amplitude for 3 scalars? What could it be? No spin, nothing. Just 3 scalars. For 3 scalars, the amplitude can just be a constant. See, that's it. Now, you might say, well, wait, I can write down zillions of terms in a Lagrangian, okay? I could write down phi cubed. If I go back to Lagrangian, I could write down phi cubed. I could write down phi squared, box phi. I could write down d phi, phi. I could write down zillions of things. Okay? Every one of those things on shell is a constant. Okay? The box phi would be 0 if the particle is massless. It would be m squared phi. It would be phi cubed again. Every one of those things, when you put the particles on shell, is a constant. So we don't need to write them down. We just know ahead of time that the amplitude is a constant. Now, let's do the next interest example. Let's imagine we have a massive spin 1 particle. So if we have a massive spin 1 particle, the first thing to do is to think about how we should describe this guy. And here I'm going to use a little bit of a hybrid picture. Normally we think that we should describe a massive spin 1 particle with some polarization vector, right? There's some polarization vector, epsilon nu, and there are 3 possible polarizations. So already we have a little mystery here, is that there are 3 polarizations that we can have, but epsilon nu has 4 components. right? So how do we deal with the fact that if we want to describe just the three physical components of the polarization vector, what do we have to do? We have to say that this epsilon isn't random. It satisfies that p mu epsilon mu is equal to 0. Okay? When we think about that, that does exactly what you want. In its rest frame of the particle, it says that epsilon only has components in the spatial directions, and that's what you naively think of as the polarizations, right? Okay, very good. So that's what we're going to talk about. We have a massive spin 1 particle. It satisfies that it's transverse in that way. And now I want to write down what the amplitude can be. Now it looks like I have more choices because I can now dot epsilon into some combination of P1, P2, and P3. There's no kinematic invariance still, but the most general thing I can do is write down epsilon mu times, A P mu, P1 mu, plus B, P2 mu, plus C, P3 mu. Okay? There's nothing else I can do. Now what is this? First of all, this last term is 0, because P dot epsilon is 1, 2, 3. The last term is 0 because P dot epsilon is equal to 0. So this is epsilon mu, A P1 mu, plus B P2 mu. But remember, P1 plus P2 is equal to minus P3. So the combination in here, though, would be P1 plus P2 also gives you 0. Okay, so the only piece that you have left is a piece proportional to P1 minus P2. All right, so we know without any work that the most general amplitude we could have for three particles is epsilon mu, again up to a constant, maybe I'll call it G now, P1 minus P2 mu. Right. And actually we notice some interesting things, that this is antisymmetric in the particles 1 and 2. If I just exchange them. So that means that if these particles are scalars, they have to carry some other quantum number, otherwise this would violate both symmetry. And that's in fact correct. We can have a coupling of a massless spin 1 particle to a charged scalar, which has two states, but not to a single neutral scalar. Okay? This would violate both symmetry. Alright. So then what is the so this clearly generalizes. So, what about a massive spin 2 particle? Then that's some epsilon mu nu. Now this has to satisfy, again, that it's transverse. And there's just one new thing, which is that, that it's traceless. So that if you take eta mu nu, epsilon mu nu is equal to 0 as well. Okay? Why do we have to say that? Because that's what throws out the scalar components out of that big tensor. Okay? So in fact, the general description for a spin S particle would be a polarization vector epsilon mu1 through mu s, for a boson anyway. And it's transverse, so P mu, epsilon mu, all the rest of these equals 0, and it's traceless. Eta, for any two indices, eta mu I, mu j, epsilon is equal to 0. Okay? Mu I, mu j. And it's, epsilon mu1 through mu s is symmetric in all these indices. Okay, so we have a symmetric tensor that's transverse and traceless. Okay? That's the polarization vector, polarization tensor for a general spin particle. Any questions about that? All right, so that's really cool. The three-particle amplitude is nailed up to a constant. We didn't have to write down Lagrangian, we just have to write down what the three-particle amplitude could look like. All right, so now we're not done. So now we just have one final thing that we have to do. We have to work out the polarization sum. So now all we have to do is see on a pole what we have to get is, if there's some polarizations landed here, we have to get the sum over all these polarizations of this coupling here and that coupling there. So it would be P1 minus P2, let me write it this way, mu1, P1 minus P2, mu s, P3 minus P4, nu 1 through P3 minus P4 nu s. And then a sum over the polarizations of epsilon, now that polarization lambda, mu 1 through mu s, epsilon lambda nu 1 through nu s. And then there's some g squared here, right? Whatever the coupling was, it's squared on this side. Okay. Now, what could this possibly be? What could this sucker possibly be? Well, all we can get is etas, just etas. Okay? That thing is going to be a buttload of eta. It'll be eta mu 1, eta mu 1, nu 3. We'll have a bunch of terms like that. But remember that the polarization vectors have got to be traceless as well. So because they're traceless, they also have to contain pieces that would just have like eta mu 1, mu 2. Because they have to take out the traces. They have to make sure that whatever this thing is. So this is some giant tensor. This is some giant tensor that's symmetric in all the mu's, symmetric in all the nu's. It's just built out of etas and nothing else. And it has to be traceless in any pair of just mu indices and any pair of just nu indices. Okay? Okay, so now let's think a little bit about how we can make that, how we can work out what that is. Let's go to the rest frame of this particle to do this calculation. Okay? We'll go to the rest frame. In the rest frame, life is very easy because the transverse condition of the rest frame of the intermediate particle, or the center of mass frame. Because the transverse condition is just telling you that this epsilon only has spatial components. Okay? And furthermore, what is P1 minus P2? P1 minus P2 is some vector in the direction of the beam. And so this is P1 minus P2. And P3 minus P4 is, so if I have P1, P2 to P3, P4, okay, that's what P1 minus P2 looks like. This is what P3 minus P4 looks like. Okay, so I just have two vectors, P1 minus P2 and P3 minus P4. Okay? And it's just those things that are going to get dotted into each other. So in the rest frame, this thing looks like, let me write it now, it says xi1 through xis, yj1 through yjs, and now something that is a bunch of delta deltas. So delta I1, J1, delta IS, JS, plus more terms, and then minus terms that look like delta I1, I2, delta, okay? It just looks like a bunch of delta deltas. None of these coefficients are right yet, but I just want to make it clear it's just a bunch of contractions of the deltas with each other. X is just a vector P1 minus P2. Y is just a vector P3 minus P4. Okay? So whatever this is some giant tensor. Let me just write it out. Let me call this tensor T. I1 through IS, J1 through JS. But what's the magic of this tensor? What's the only important property that it has? T is symmetric in all the i's, in the i's and in the j's, and traceless. And that's the tricky part. Traceless in just the I indices, in i's, in pairs of i's, or pairs of j's. And if you do this by hand, if you just do it by hand for spin 1 there's nothing to do. Right? For spin 1 there's nothing to do because there's just one index. So this tensor is just delta ij. Nothing to do. For spin 2, you can start doing it by hand and take out the traces, but that's where it starts getting to be slightly painful. Alright. But see, whatever this is in the end, whatever this is, it's just, again, a sum of a bunch of pieces with a bunch of x dot x's. We'll just get a bunch of x dot x's to some powers y dot y's and x dot y's. Right? That's all I'm getting out of this. All right. Now comes the next observation. So far we're talking about this like a particle physicist, right? We're summing over polarizations. This is going to turn into the partial wave expansion that you're used to from quantum mechanics. But the partial wave expansion is all about expanding solutions of a point potential, right? So you look at so how are these things related to each other? They're related in a very, very pretty way, which is how do you know whether if someone handed you this function, how would you check if they handed you the function as a function of the x's and y's? What is a simple way you could check that it came from something that was traceless? It's exactly the traceless condition. The traceless condition is the same as that if I take the Laplacian of this in x of this function, it's equal to 0. Okay? So why is that? Because this is saying take d by dxi, dxj, delta ij. But taking d by dxi, dxj is just pulling out tij. And then so I'm just delta ij in it, saying that for anything that I take out, it'll be traceless in those indices. Okay? So the traceless condition is exactly that Laplacian of f is equal to 0. And therefore, there is a beautiful way of generating all such functions for all such spins in one go. Okay? So obviously the answer is unique. For any spin that you have here, there's just one possible tensor that you can get. So all I have to do is write down a solution of the Laplace equation that contains all these functions with all amount of powers of x and y, and then I just pick off the coefficients one by one, and I have the answer. So how do we do that? We just write down a solution of Laplacian f equals 0 if we're in d spatial dimensions. If we're in d spatial dimensions, the solution is 1 over x minus y to the power of d minus 2. Okay? That's the solution of the Laplace equation in d dimensions. And let's just expand this in powers. Imagine y is small compared to x. We're expanding. If we're expanding in powers of y, this would be 1 over the magnitude of x to the d minus 2. And then a sum over y over x to some s times a function, which I'll call g d of s of cosine theta, the angle between x and y. Okay? And this function, if I think of it as a function of cosine theta, if I take out just the overall lengths, that's exactly the same function. So this numerator, this polarization sum, is exactly given by these functions. Okay? See, by construction, this is something, if I take the Laplacian in y, let's say, of this top thing, it manifestly gives me something with exactly the right number at spin s, has the right numbers of y's, and therefore it has to be the right answer. Okay, so now these objects are called, in d dimensions in general, they're called Gegenbauer polynomials. But they're just the generalization of the familiar, Lejeune polynomials in 3 dimensions, and even in 2 dimensions, the even more familiar cosines. Okay, so we've learned something then. We've learned what the answer can look like. If you have a particle of spin s, if you have a particle of spin s, if you're assuming a particle of spin s, then the amplitude in the neighborhood of the resonance it has to look like 1 over s minus m squared times g squared times that Gegenbauer polynomial, if you're in d dimensions and it has particle spin s, of cosine theta. So that's what it has to look like in the neighborhood of the pole. And if you want to convert this to more familiar s to u variables, you just have to remember the relation between p and s in the scattering angle. This is a little exercise I'll leave you to work out for yourselves. But if external particles have mass little m, this is the external particles, external scalars. I'm mapping it all identical here. Okay? Then p is s hat minus 2m squared times cos theta minus 1. So if you want to write everything in terms of p, then you could say cos theta is 1 plus 2t over s minus 4m squared. And you therefore, and s is, again, we're only interested in the neighborhood of s equals capital M squared here. So we then learn that, on the pole, it has to look like g squared over s minus m squared times this Gegenbauer polynomial of 1 plus 2t over m squared minus 4 over m squared. Okay? And we know exactly what these guys are. In fact, let me just tell you a few of them. The first few, and just by doing this, just by expanding this out explicitly, you can see what they are. But in any number of dimensions, this for the spin equals 0 of cosine theta is 1. For spin equals 1 of cosine theta is cosine theta. And for spin equals 2 of cosine theta, that's the first place where d matters, and it's d times cos squared theta minus 1. And then you can find it. All right. So we've now learned what can the most general 2 to 2 scalar amplitude look like. The most general 2 to 2 scalar amplitude can look like polynomials in S, T, and U, just the contact terms that we were talking about before, plus things that look like g squared sum over spins and species and so on of g squared S I times the Gegenbauer polynomial. I'll just keep it writing in terms of cosine theta here, over S minus m squared. And then perhaps we have the other channels. We might have p channel particles and u channel. We have them. And so that's the most general thing. Notice that there's a very interesting constraint here, especially if the particles are identical on the outside, that the coefficients of those Gegenbauer polynomials are positive numbers. They're g squared. Okay? So it's not guaranteed that any old function of S, T, and U that you write down can be consistently interpreted as producing particles in a physical way, in a way that's compatible with unitarity. The fact that those coefficients are positive is unitarity. This whole thing is checking unitarity. Let me give you just as a very quick detour and application of this. Just a small aside, and then we'll get on. But this is where these things became. This was one of the motivations for some of us is to start revisiting these things. I'm going to write down a very famous amplitude on the board for you. Okay. It's very famous in the 1960s. And this is how string theory was born. We're going to write down the Veneziano amplitude. The Veneziano amplitude was a function just of s and t, and it's gamma of minus s minus 1, gamma of minus t minus 1, over gamma minus s minus t minus 2. And I'm working in some units where some string scale has been set to 1. Okay, so otherwise I'll put s over n squared and t over n squared, but just not to pollute things all the time. I'm not putting that to 1. Okay. Now, if you remember anything about the gamma function, the gamma function has poles. Gamma of x has poles when x equals 0, minus 1, minus 2, and so on. Okay? And therefore, this has a pole when minus s minus 1 is equal to 0. So it has a pole when s equals minus 1. Okay? So it has a first pole at s equals minus 1, which is negative. That's bad. That's the famous tachyon. So that's the fact that Veneziano amplitude has a tachyon. But never mind. Okay, so it has a negative mass squared, but for the purposes of our arguments, that won't be relevant. But anyway, so the particle that we're scattering has mass minus 1. Okay? So our m squared for our external particle is equal to minus 1. Let's remember that. Okay, now someone hands me this function, and people were very excited about it. You explore this, you explore that. It's exponentially soft. It has these properties of duality that you can expand it in the S channel or the T channel. People played with it for quite a while, but it actually took them a number of years to check that it was at all physical. By which I mean, is it actually unitary? Does it satisfy that it's actually unitary? This is actually a good example of something that, as we'll see in a moment, it's not automatically unitary. It doesn't automatically make sense. We'll just use it as an application of our general formalism. So let's go to the next pole. See, all the difficulty is supposed to be on the pole. You have to be able to interpret it as a positive sum over these Gegenbauer polynomials, right? With positive coefficients. It's that positivity that we have to check. Let's go to the next pole. The pole at s equals 0. On the neighborhood of s equals 0, this looks like gamma of negative t minus 1 over gamma of negative t minus 2. So this is as s goes to 0. Now the only other thing you have to remember about the gamma function is that x gamma of x is gamma of x plus 1. And so this pole, the residue on the pole is 2 plus t. Okay? So it's like 2 plus t. T plus 1 is 2 plus t plus 1. So that's why we get some 2 plus t upstairs. Okay, that's okay. That one turns out to be totally okay. Let's look at the next residue. There's a pole at s equals 1. Okay, so s goes to 1. We have gamma of negative t negative 1 over gamma of s goes to 1, negative t, what am I doing? Minus 3, thank you. And so the residue is 2 plus t times 3 plus t. And so on. Okay? So the residue at s equals n is 2 plus t. The residue is 2 plus t, 3 plus t, up to n plus 2 plus t. Right? But let's stare at this guy. That's the first interesting guy. This turns out to be fine. Let's look at that. It looks harmless enough, just 2 plus t, 3 plus t. But we have to ask, what is it as a function of cosine theta? Right? So, remember, t is equal to s halves minus 2m squared times cos theta minus 1. S is equal to 1 on this pole. Remember, m squared is equal to minus 1. So this factor is 1 halves plus 2, which is 5 halves, times cos theta minus 1. Okay? And so what is t plus 2 times t plus 3? T plus 2 is 5 halves cos theta minus 1 half, and t plus 3 is 5 halves cos theta plus 1 half. Okay? So this is 25 quarters cos squared theta minus a quarter. Okay? So, but we're supposed to see that we can write this as a sum over those Gegenbauer polynomials with positive coefficients. Remember, what do they look like? they look like for spin equals 0, it was 1. For spin equals 1, it was cos theta. For spin equals 2, it was d cos squared theta minus 1. Okay, in d spatial dimensions. So clearly, there's a spin 2 particle here and a spin 0 particle. No spin 1 particle, because there's no cos theta p sitting here, right? But you'll notice that we're in trouble, because it's 25 quarters times cos squared theta. I can write it as 25 quarters times cos squared theta minus a 25th. But let me write that as minus 1 over d plus 25 quarters times 1 over d minus 1 over 25. Okay. Now, this thing, cos squared theta minus 1 over d, that has a positive coefficient. That's good. That means that that's a spin 2 particle that I'm exchanging with correct sign. Good. But this is a spin 0 particle that I'm exchanging. And you see that if the number of dimensions of space is larger than 25, the coefficient is negative. Okay. So it's inconsistent. You can't just write down any old amplitude that you want. You can get things that violate unitarity. Okay. That's how you discover that string theory needs to live in less than or equal to 26 spacetime dimensions. Okay. Okay. All right. So that's just one application that you can't, not anything goes, right? You can't write down a random function. We know what every function, every possible consistent tree level like scattering amplitude, what it looks like. And there are certainly possible to write down examples that violate. All right. Any questions about this?
This is all naked tree level.
Yeah, it's all tree level. Yeah.
If we consider order and two and
yeah, then, but if it, you see, if it's bad already at low orders, it's not going to get better at the high orders. Okay. So. Yeah, I mean, in general, remember, we're talking about, yeah. Okay. So, what I hope you got from this first part of the discussion was that all the action is in thinking about what the 3-particle amplitude looks like, and that it's very constrained because there's no kinematic variables that anything can depend on. So we should first figure out what the 3-particle amplitudes look like. And after we do that, we know what check we have to do at 4 particles, because on the poles they have to factorize consistently into the product of the 3-particle amplitudes whose structure we just will have spent some time determining. Okay, so that was the invitation, and now let's move on to part 1. Don't worry, you all. Just chill. It's gonna be okay. So part 1 is dealing with massless particles. And our goal here is going to basically be to determine what the to learn how to think about massless particles and determine the what the 3-particle interactions look like. Probably what I'll do in I have half an hour, right? Or 20. Probably in the half an hour I can just set up at least what the challenge is and just start doing it, and then we'll spend most of the day tomorrow finishing the story for both masses and massive particles, just so default doesn't start. Okay. But first, before jumping in and telling you about these spin helicity variables and so on, let me again go back to the more familiar ways of talking about things and explain what is the challenge. What is the challenge when you have massless particles? There's no challenge when there are scalars. The challenge is when we have massless particles with spin. Okay? And that's because of a famous fact. This amazing fact has driven particle physics for, and it's, depending on how you think about it, for almost 80 years. Okay? Is this fundamental difference between the number of degrees of freedom of massive particles and massless particles. Right? Massive with spin. A massive spin 1 particle has 3 degrees of freedom, while a massive spin 1 particle has 2 degrees of freedom. Right? And it's because you can't go to a frame where the massless particle is at rest, and tilt your head and see it spinning in every possible direction. Right? The basic fundamental difference is discontinuous difference between masses and masses. Okay? That's the heart. That's really the heart of what the challenge is in talking about massless particles. On the one hand, it's also what makes the existence of massless particles with spin natural. Okay? Why is it that we obsess about a hierarchy problem for the Higgs, but no one asks why is the photon massless? Okay? Now, if I were to ask you why is the photon massless, what answer would most of you give? Why is the photon massless? Okay, the answer most of you would give is that the photon is massless because of gauge invariance. And in fact, from the point of view of what I'm talking about here, and you'll see this more and more powerfully as things go on, that answer is almost exactly wrong. Okay? It's almost as wrong as it could be. Okay? It's almost opposite of the truth. Okay? Now, I'm exaggerating a little bit, but what's really going on is that because the photon is massless, human beings invent this notion of gauge invariance as a useful crutch for describing their properties. It is not a property of nature, it is a property of human beings, theoretical physicists in the 1930s and 40s and 50s. Okay? Gauge invariance is not a property of the universe. It's a property of the imagination of theoretical physicists. Okay? And in fact, the physical explanation why is the photon massless is that 2 is not equal to 3. Okay? Because we have this discontinuous difference between the degrees of freedom, imagine, no, this is serious. Imagine in some approximation the theory was free and you managed to get a massless spin 1 particle. Now turn on interactions. You cannot all of a sudden make it massive. It's like being a little pregnant. It's not possible. You either are or you're not. Right? So you can't just invent a degree of freedom out of nowhere. Okay? That's the reason why once you have a massless spin 1 particle or massless spin 2 particle, their existence is robust. They're completely insensitive to changing any parameters of the theory because of that discontinuous change in number of degrees of freedom. That's why there's a hierarchy problem for massive, for spin 0 particles, because 1 is equal to 1. There is no change in the degrees of freedom between massless and massive when it comes to spin 0 particles. That's why the Higgs is so damn special, because we've never seen an elementary particle with spin 0 before, and that's why learned theorists would say for ages there's a good reason we shouldn't see them. It's exactly because of this. In condensed matter systems, just to give you an example, we can engineer things which at long distances give you things that look like gauge fields, massless spin 1 particles. Okay? And why? Why can we do it? Of course, not any old random material does it. This material doesn't do it. You have to get in some basin of attraction of the right kind of material, but once you get it, you can do anything you want to it. You can tweak it, you can put it under pressure, you can heat it, you can do anything you want, and you're not going to change the fact that this happens. Right? Whereas if you try to do the same thing to get a scalar, you never do. Okay? And that's because this argument has some teeth to it. Okay? So gauge invariance is not a property of nature. It's a property of how human beings go about describing nature. And we see it very vividly in this polarization vector language. I want to talk about it for 5 minutes here, just because when we get to it tomorrow, you all, because we won't do it today because you're so hungry. Okay? When we get to it tomorrow, we'll talk about things in a totally different way, where we don't even talk about polarization vectors. Okay, but let's remind what the problem is in polarization vector language. The problem is that we said that we want to describe a massless photon. It has momentum p mu. We want to describe it with a polarization vector, epsilon mu, but there's 2 degrees of freedom here, right? Not 3. So what can we do? Well, the first thing we'll do what we did before. We'll say that p mu epsilon mu is equal to 0. That's what we did when it was already massive, right? So that takes us from 4 to 3. But there's nothing we can do in a Lorentz invariant way to take it from 3 to 2. Okay? There's simply no way of taking it from 3 to 2 in a Lorentz invariant way. So what I'm saying is that really the photon, so let me say this a little bit more, slightly more conceptually, really the photon has some helicity, h. And really we imagine that there's such a thing as a polarization vector, epsilon mu, that depends on h. Okay? We even remember what they look like. We'll even write them down in a second. But first of all, why do we do that? Let's remind ourselves what we do that. You see, the real amplitude, the actual amplitude, just depends on helicities and momenta. That's what the amplitude depends on. P1 through Pn. That's what the amplitude actually is. Right? However, when we calculate it using Feynman diagrams and Lagrangians and so on, we say that this is some polarization vectors that depend on the helicity, mu1 through epsilon mu n hn, and mu1 through mu n. That depends on the p's. Okay? This is what we calculate with Feynman diagrams. And then we have to dot it into polarization vectors at the end to get the actual amplitude. Okay? This is, by the way, why most of you in courses have never seen an amplitude. You've never actually seen one. You've even computed Feynman diagrams, but the last crucial step, you dot into polarization vectors. How many of you have actually done it to see what they actually look like? You don't do it, right? What you normally do is you mod squared, you do polarization sums, right? That's fine, but an actual amplitude, this helicity plus, minus, do you ever see it? Have you seen one? How many of you have you seen one? Okay. Great, a small minority, right? Okay, so now, so the reason we do this is that the amplitudes aren't actually Lorentz tensors. What you get from Feynman diagrams are Lorentz tensors. But the amplitudes don't have the symmetry properties of Lorentz tensors. What do they have the symmetry properties of? What they are things that if you do a Lorentz transformation, if you do mh1 through hn, if you do a Lorentz transformation on the momenta, you should get a phase that depends on the helicity. This is what the symmetry transformation properties of amplitudes should be. Okay? This phase is the famous little group. That's the famous of the in Wigner's way of classifying how Lorentz transformations act on particles. He talked about the little group. If you have a massive particle, the little group is just rotations. If you have massless particles, the little group is just the rotation around the direction in which the particle is moving. So phase factor you can pick up in the direction in which the particle is moving. Okay? And that's what tells you the helicity of the particles. That's why the only quantum number we have is the helicity. So amplitudes are not Lorentz tensors. Feynman diagrams are Lorentz tensors, but amplitudes are not. That's why we pretend there is such a thing as a polarization vector that soaks up the Lorentz indices and converts them into little group indices. Okay? And that would be awesome if those objects existed. For massive particles, they exist. We talked about them, right? There are these epsilons, p dot epsilon equals 0. That's great. But for massless particles, they do not uniquely exist. There is no such thing as the polarization vector that goes along with a given helicity. Okay? Well, we've seen abstractly why it is, because we just can't think of any other transformation property, any other constraint, nothing else to do. There's no way, nothing else we can do to go from 3 to 2. Now, before telling you the answer, you're probably many familiar with this, before telling you the answer, let's just cut the crap here. All this bullshit you're talking about, I know what polarization vectors are. Screw you. Okay? P mu, when the particle is moving in the z direction, the polarization vectors, and I even know what they are for plus or minus helicity, because I'm so smart. They're 0, 1 over root 2, plus or minus I over root 2, 0. Right? Aren't those polarization vectors? Yes. Everyone agrees, right? Those are the plus or minus helicity polarization. What the hell am I talking about? No polarization vector. Just wrote it down. Right? Now, you see I've made a little choice here to put zeros there and there. Right? That's not a Lorentz invariant choice. And I can convince you it's not a Lorentz invariant choice, and you can convince yourself by doing the following little exercise. And I encourage you to do this exercise. It's very simple to do. Okay? Let's say you take p mu, the momentum, and you rotate a little around the z-axis. So now the particle is moving this way. You boost in z, you rotate back, and then you boost back. That's a series of Lorentz transformations that you can do that takes p mu and brings it back to p mu. So on p mu it has done nothing. Okay? Now just do that on epsilon. And I promise you by the time it comes back, it will not look like that. Okay? Instead, where there are zeros, there'll be something non-zero, and they'll be equal to each other. Okay? So if you do a sequence of Lorentz transformations, that brings lambda that brings lambda p back to p, lambda epsilon will not go back to epsilon. So it's bullshit. They're not Lorentz invariant objects. Okay? You're fooled into thinking they are because you write down indices, but it doesn't mean that they are. Right? What are they? What are they? But what happens? It's not arbitrarily terrible. What happens is that lambda epsilon mu is epsilon mu, and it at most differs by something that might depend on p times p mu. Okay? And that makes sense when the particle is massless, because it continues to satisfy that p dot epsilon is equal to 0, right? So if this is epsilon prime, p dot epsilon prime is still equal to 0 because p squared is equal to 0. Okay? Is that clear to everyone? So in order to describe in this language massless spin 1 particles, we have to introduce a novel concept that we weren't forced into for anything before. We have to say that the physical states aren't associated with a polarization vector, but they're associated with a whole equivalence class of polarization vectors. Any two polarization vectors that differ by something proportional to p mu have to give you the same answer. Okay? So that's the crucial thing. And that's why if you and that's why describing massless particles with spin, starting at spin 1 and higher, is so challenging. So what we've learned is that really Lorentz invariance is telling us that there's a whole equivalence class of polarization vectors epsilon mu that are identified epsilon mu plus anything times p mu, and they should give us the same amplitude. Otherwise, when we dot them into polarization vectors, we won't get a Lorentz invariant answer. When we dot the polarization vectors into m, we won't get the same answer. That means that if you want to use this formalism to describe massless particles, you have to have that m mu, mu2, whatever, mu n, that p mu dot this has got to equal 0. So this is the constraint. If you come up with rules for building these m's, if you dot into a polarization vector and then you shift epsilon by anything proportional to p, that piece has got to give you 0. Right? Otherwise, you're not going to get an answer that's actually Lorentz invariant. That's why you have to work hard to come up with underlying Feynman rules that guarantee that this happens. Okay? Now, in this opposite way of thinking about things where you start worshipping gauge invariance and thinking about the Lagrangian and so on, this is called the on-shell word identity. Okay? So this is the consequence. But from this point of view, we're starting from the bottom up. That's the theme of these lectures. We're trying to build the objects that have the correct physical properties directly. And already here, we shoehorned ourselves into this description using polarization vectors. And we see if we're going to shoehorn ourselves into this description, we had better make sure that whatever the rules are that give us those m's guarantee that if I shift epsilon by epsilon plus something times p, that I get the same answer. Now, why is that even roughly related to gauge invariance? What does that shift look like in position space? Okay. A mu goes to A mu plus P mu something. Okay. And that's the beginning of why, if you want to use the Lagrangian and Feynman rules in order to describe these particles, it's perfectly good idea to do that, right? You have to make sure that this happens and not a random Lagrangian will do. And it's a very nice exercise that you can play with. I won't do it here. I think I did some of this exercise in some lectures I gave at TASI earlier this year, so maybe they're online if you want to see what some of them look like. You can see them there, which is again in the somewhat in between spirit of doing things, where you just start off life trying to write down the Lagrangians, okay? But you don't care about it. You don't care about, it's always easier to ask for a forgiveness than for permission, okay? So I want to describe, let me just sketch out what I did and then you can look at it online. But you want to describe massless spin 1 particles. let's just do it, right? What I want to do, remember, what I want to do is I want to generate these mu1s through mu_n, right? And I'm going to get this from a Lagrangian. I'm going to get it from Lagrangian and Feynman rules and so on. And I'm going to dot them into polarization vectors at the end, just like what we normally do. Except now I know what I need to make sure happens. I need to make sure that this p mu is equal to 0. That's my guiding principle, because if that doesn't happen, I am screwed. I don't get something Lorentz invariant. But other than that, I don't care. People tell me, oh, it should be gated f mu. I don't care about f mu. I've never heard of f mu. I want to build some rules. So I say there's something like that. I say, oh, that propagator is a to mu nu over p squared. Fine. Okay? If I want to get that out of a Lagrangian, I would just say that the Lagrangian is d mu a nu d mu a nu. Okay? That gives me the propagator. Okay? You say, oh my God, it's not f mu squared. Screw you. I don't care. Right? Then just to say how screw you I'm being, what could the interactions be? The first interaction I could write down is like a nu, d rho, whatever. A, dA. I can have interactions that look like that. Let me put a G here. I can have some G prime, A, and so on. Okay? And at least here, these are both dimensionless. Right? Okay, so I wanted to start with these dimensionless interactions, and that's it. Right? So I'm going to calculate amplitudes with this guy. By the way, or I could write down, just here, I could write down, if I have a fermion, I could just write down psi bar gamma mu psi a mu. Okay? That's the only thing I can do. Okay? There's some G double prime there. I just write down everything. I don't care about gated invariance. I just write things down, right? By the way, what are these Lagrangians doing for you? What Lagrangians are doing for you are a way of producing these amplitudes that at least have roughly the correct properties, that the only singularities they have are poles that look like 1 over p squared. Right? That's the real point, is that the Feynman rules are making the locality of the interactions manifest in space, and that means that back to the actual amplitude, they can manifest that the only poles occur when things like p squared go to m squared or p squared goes to 0. That's why it's a good idea to play with Lagrangians, because that much is guaranteed to come out. But we need more. We need these more refined things. We need to make sure it's actually Lorentz invariant. We need to make sure that condition is satisfied. And this is the exercise that I did in the TASI lectures. You can just go through and beautifully derive gauge theory. Derive why the G and G prime and G double prime and all those things have to be related to each other, and why you need the Lie algebra structure and all of that stuff. You've never heard of it, and it just comes out of the requirement of finding something that's actually Lorentz invariant. Okay? So it's not like you start with this idea that it's, oh, global symmetries suck, local symmetries are so beautiful, you do it separately here and there, and it's so beautiful and nice. And that's in fact, in a quite specific sense, that it's actually empty, because you can take any theory and turn it into a theory that has a local gauge symmetry if you add degrees of freedom. And that's because ultimately, you see, what gauge symmetry really is a redundancy. And here it's as manifest as possible. It's a gauge redundancy. This is just our... It's not a symmetry. It's saying that all these different things are actually describing the same physical state. Right? It's like different relabelings of the same thing. A symmetry is something that takes one state and converts it to a different state. Okay, symmetries do useful things. Symmetries, for example, tell you why, if you have a rotationally invariant system, it tells you why a bunch of energy levels will be degenerate with each other. Okay? Because it takes one state and it turns it into something else. This isn't a symmetry, this is a relabeling. It's a convenient relabeling, and it's a convenient relabeling that's convenient in one particular approach to trying to write down amplitudes with a consistent property. Okay? Okay. Now, actually, since I'm in this neighborhood, and since I only have 5 minutes, let me just give you a more familiar example of a redundancy, just to really drive home how content-free it is. And then next time we'll start with a different language, just from the very beginning, with a different language for describing the amplitudes. But let me just give another example of a redundancy. Actually, these are much more elementary examples, but these are maybe examples that you're familiar with in physics. Okay, let's say we want to talk about a point particle that's moving in space-time. Ordinary, but relativistic particle, right? How do I describe, I have time and space, I have x and t. And if I want to describe a particle moving in space-time, well, I do it like I always do. I have to give you what is its x as a function of t. Right? That's the actual information. The actual information is 3 variables as a function of time. Right? Now, of course, by choosing a time, I'm picking out a frame. That's just life, right? But if I want to, in a given frame, that's how I have to describe it. And so, what is the Lagrangian for this relativistic point particle? Okay. The Lagrangian for a relativistic point particle is, or the action, let's just say, let me actually write action better. The action is integral dt, root 1 minus x dot squared. The minus sign. Okay? And that's what it is. That's what it actually is in terms of the direct physical degrees of freedom. X is the dynamical variable. X is a function of t. T isn't the dynamical variable, right? X is the dynamical variable, and that's what the action is. Of course, when you write it that way, it doesn't look super Lorentz invariant. We see the gamma there, that might make you happy, right? But if you have to check, how does this transform into Lorentz transformations? Then okay, you have to check, and it's the Lorentz invariant. But it's not manifestly Lorentz invariant. And that's not the way most of us remember the action for a point particle. How do most of us remember the action for a point particle? The way that we normally talk about it is we say that no, what's going on is I have some x mu as a function of tau. Nice tau. Now it's x mu. Everything looks very nice. Because x mu is a function of tau. Okay? Now what is this tau? So in other words, this is telling me the function of here's tau equals 0, tau equals 1, tau equals 2. It's just telling me where the t and x for the particle is at any tau along the trajectory, right? So that's the usual way that we more fancily talk about a point particle moving in space-time. And in this way, we say that the action is just integral of the proper distance, right? So the proper distance is root dx mu by d tau squared. The minus tau. Okay? And isn't that beautiful? In that picture, the Lorentz invariance is manifest. Okay? Right? The integral d tau. Okay, but in this picture, I have too many degrees of freedom. x0 isn't independent of x1, x2, and x3. Okay? So I've made the Lorentz invariance manifest at the expense of enlarging the set of things that I'm talking about. Right? I'm no longer just talking about x. I'm talking about x and x0 altogether as x mu. And my action has a redundancy. Okay? This action has a redundancy. In fact, if I replace tau by any function of tau, then the action goes into itself. That's just saying that this tau is a totally garbage, human, arbitrary invention of how we choose to label the points on the same path. Right? We can do it in any way that we like. They're all going to give us the same answer. So there's an infinite symmetry. Wow! It's a gauge symmetry. It is a gauge symmetry. It's a local gauge symmetry. It's diffeomorphism invariance. My God, general covariance, so beautiful. Okay? It's a bullshit symmetry. Right? It has no content. Okay? It's a purely, completely a human construct. It's not anything, it's not anything real. Okay? So we've seen redundancies before. They're very useful. They're incredibly useful. There's nothing wrong with them. They're incredibly useful. The simpler things that we see redundancy, if you try to describe the equation for a circle, right? That's also a situation where we introduce redundancies. In order to do it in a way, if you want to officially describe the manifold that's a circle, you have to use two charts to cover this part of it and that part of it. Okay? If you want to talk about something that talks about as a single bigger whole, you have to introduce more variables with a redundancy. You say that it's x is cosine t, y is sine t, but you can replace t by t plus t cubed, and that also covers the circle. So there's a huge redundancy. Same thing, exactly the same thing. This situation happens to us over and over again, that in order to bring out some competing aspects of the nature of the physics, it's useful in some languages to introduce a redundancy. Okay? This is the gauge redundancy of diffeomorphisms. And I hope you agree that it's useful, but as a property of human beings, and the particle itself knows nothing about it. Okay? And similarly, the story with the gauge redundancies for the description of massless particles with higher spin is essentially identical. All right, so what we've seen in this lecture, in the first part, is that just in the invitation, in thinking about the interactions of just scalars on the outside, that it's possible to be very explicit about any possible thing you could get. If you wanted to know 2 Higgses to a spin 7 particle coming back out to 2 Higgses, you know how to write down the answer now, right? You just write down the 7th Lejeune polynomial, you expand that 1 over x minus y thing out to the 7th order in Mathematica, okay? You pick out the appropriate coefficient, you shove it upstairs in front of 1 over s minus the mass of the resonance squared, and you're done. Okay? So you can do that. We saw how constraining it is, how you can discover that string theory only makes sense in 25 dimensions or less from requirements like that. So that was an invitation to think about these on-shell 3-particle amplitudes, not talk about Lagrangian, and try to directly build the physics directly from the physical requirements. And then we've reviewed why doing that is challenging from the standard perspective. And why we're forced into introducing gauge redundancies in order to do it. By the way, those redundancies are why you have 50 pages of algebra for 2 to 3 gluons and 100 pages of algebra for 200 pages of algebra for 2 to 4 gluons. Is because the binary diagrams are dragging around these enormous redundancies everywhere they go in order to make the locality and unitarity of the process as manifest as possible in this language. Okay? So what we'll do tomorrow is go right back to basics and find the actual variables the amplitudes are functions of. The amplitudes are not functions of momenta and polarization vectors, or they're only redundantly so. Okay? Well, we'll talk about what amplitudes are actually functions of. And when we see what amplitudes are actually functions of, then we can begin the process much more simply and more systematically. Start with 3-point functions, determine 4-point functions, discover all the consistent theories that are known and why all the inconsistent theories are inconsistent, and end with a computation of some cool massive amplitudes in both the standard model and beyond. All right, thanks a lot.